Hello and welcome to video 1 of 2 for Chapter 7. Now, Chapter 7 deals with what's called electric potential or voltage. And we're going to talk about that. But before we talk about that, what I'd like to do is to take a look at the simplest charge configuration that you can have. That is that of a point charge. And I'd like to look at the associated potential energy. Now we know, from University Physics 1, that anytime you have a force present, you can talk about work. So that's where I would like to start, is the relationship between the electric force and the work that it produces. So, uh, imagine a situation where you have a point charge. We'll say it's positive, just to make our life easy. That sits at the origin of a coordinate system, so we're not saddled with weird vectors or anything like that. So here's my positive a point charge. I'm going to call it capital Q. Now, what I'd like to do is to take another charge, which we generally call a test charge. We call them test charges because it allows us to test the characteristics of the electric field and also of what we're going to discover is the electric potential. So what I'd like to do is to take a point charge way out over here, which I'll call QT for test. That's positive as well. And I'd like to bring it in, maybe to about here. So if I were to draw a vector, or rather a line that sort of connects the two, our starting point is going to be right here, which I'll call R naught. And our ending point is going to be about here, which I'm going to call R. Now, so the electric force we know between these two is going to look something like this. 1 over 4 pi epsilon naught Q times QT divided by the distance between the two, which we're going to call R. Let's see, notationally, it's a little funny. This is R, but we're bringing it to R. And it points in the R hat direction. Okay? Now, if you remember from University Physics 1, the differential form of work looks like this. It's F dot dr. It's a line integral, or at least it's related to a line integral. Now, dr here is the positive differential along the direction that you're integrating. And we're going to do this in cylindrical, or not cylindrical, but circular polar coordinates. And so we're going to integrate along r. So this right here would be the direction of dr vector. Okay, it's in the r hat direction. Now, so what that means is, if these are both positive charges right here, that when I bring this thing in, I'm fighting this charge wanting to push it away. Okay? So if you were to think of this thing as having a velocity, or this test charge as having a velocity, and moving towards the charge at the center, it would slow it down. Now, if you remember conversations around work, when you do work and you cause something to speed up, you do positive work. When you do work and you cause something to slow down, you do negative work. So here, if you look at the dot product between F and dr, and dr here is going to be dr r hat. If you look at this dot product right here, the force is trying to push that test charge this way. But this is also the direction that we're integrating. So the dot product between these two is going to be 1. So at the end of the day, we have 1 over 4 pi epsilon naught Q test charge, Q, r squared dr. This is what we're going to integrate. Now when I integrate this from what I'll call point A to point B, to find the work, this will be the total work. That's the same thing as integrating. Big Q, little q sub t, over 4 pi epsilon naught dr over r squared. From r naught to r. Now, most of the stuff within the integrand is a constant. And I can pull all that stuff out. So my work here would be big Q, little q sub t over 4 pi epsilon naught. And what actually needs to be integrated from r naught to r is 1 over r squared. Now when I integrate this, I get minus 1 over r. So, minus sign out in front, q test over 4 pi epsilon naught, 1 over r, evaluated from r naught to r. So let's go ahead and plug those in. Minus big Q, little q sub t over 4 pi epsilon naught, 1 over r minus 1 over r naught. Now, I want you to take a look at this, right? So r naught very clearly is going to be bigger than r. I'm starting out here and I'm ending up here. So when I do these divisions, this is going to be smaller than this. So the difference between these two is going to be a positive number. You have a minus sign that sits out front. Both of our charges are positive. And what that means is I'm doing negative work. So like I said earlier, if you think of this thing as traveling towards the charge here with a velocity, this force is going to act on it to try to push it away. You should get negative work, and as you can see, that's exactly what we get. What I'd like to do now is to take these results and test basically the electrical force to see whether or not it's conservative. So let me borrow this right here. And we're going to paste it right here. And I'm going to borrow this stuff right here. And paste it here as well. All right, so what I have here is similar to the situation that we have here. We have a charge of capital Q that sits at the origin. And, it's a point charge, which means, the force that it exerts on other charges, specifically the test charge, looks like this. We're going to, assume, again, a positive charge. And what I'd like to sort of point out here is that the electrical force itself only depends upon r, that is, how far away. So if I were to, for example, think about a distance r away from our little charge, sort of center it like this, like that. That's a little better. So if I were this far away, any place on this sphere with a radius of r, I would experience the same amount of force. Now, obviously, the direction would be different. And that direction typically is defined by, how far up, we'll say, from the x-axis you are. And if you think of the z-axis pointing straight out at us, how far down from the z-axis you are. Those two angles, and then how far away. And that's how you identify, a location in space. But I just want to think of this two-dimensionally for right now. So here on this circle, if you will, at all points, the magnitude of the force is the same. But, directionally it would be different. Like, for example, here, if I had a positive charge, the force would maybe be this way. Here it would be this way, etc., and so on. So that said, let me just stitch the little circle here for a moment because I don't need it. Oh. So that said, I want to think about taking a test charge. So a little positive charge. And we're going to start it right here. So here's QT. And what I want to do is to move it. I want to move it from here to here. That is directly through along a radius towards big Q. And then I'm going to move it along the surface of a sphere of radius r. Then out this way. And then back this way. So from a direction standpoint, I want to move the charge like this. Okay. So we have 1 will be going from here to here. 2 will be going from here to here. 3 will be going from here to here. And 4 will take us back to our starting point. Now these are different distances. I'm going to use the same terminology that we did before. I'm going to call this distance away r naught. So this would be the same thing as r naught over here because it's the same distance away. I'm going to call this point right here r. And this right here would be r as well. The only difference between these two would be the angle, swept from x towards y. And let me talk about unit vectors. So, when you work in a Cartesian coordinate system, you have I, j, k, or x hat, y hat, z hat, depending upon, what type of notation you like to use. And as I mentioned, back here, you have the direction out when you work in, circular polar coordinates as being r hat. Now, there's also another unit vector as well, and that's moving along the angular direction. So I'm going to call the angular direction here theta, just to be consistent with what we're used to. And let me sort of complete this like this. This is the angle that we're walking out, if you will, from here to here. Going this way. And so you have r hat like this. And in the angular direction, in the theta direction here, you have what's called theta hat. And theta hat is at right angles to r hat. All right. So that said, I'd like to remind you about the definition of this differential work here. It's f dot dr. So let's talk about our drs. So in 1 and in 3, the force and dr line up. So this would be the direction of dr. Here, this would be the direction of the force as well. Here, this is the direction of dr. This is also the direction of the force, trying to push it away, just like it's trying to push it away over here. But along these arcs, along these sections of the circle, the force is trying to go this way. But the direction that we're moving, dr, is this way. It's actually along theta hat direction. And those are at right angles to each other. Now, if you remember dot products, the dot product right here means that you take the magnitude of f, the magnitude of dr, and then you look at the angle in between. So cosine of 90 degrees is 0. So what that means is that when you look at the work along 2 and the work along 4 are the same and they're equal to 0. And that's because you have these 90 degrees that separate the direction of the force and the direction that you're moving along the arc, okay, along dr. So really the only thing that's going to contribute to the total work here would be what's going along 1 and what's going along 3. Now the goal here is to see what the total work is around the closed loop, because conservative forces are defined by the total work around a closed path being 0. If this is true, then F is conservative. If it's not true, then F is not conservative. So the question is this true? And just to remind you, the little circle here on this integral means a closed loop. So we've already done 2 parts of the loop, section 2 and section 4. They don't matter. They're 0. So at least that much is satisfied. So let's take a look at the work for part 1. Well, we've actually already calculated this type of work. When we looked over here, we started at R0, we ended up at R, and we discovered the work looked like this. So just to remind you again, and I'll still this part too. I should have done that previously, but I didn't. Okay. So just to remind you here, for work 1, we start at R0, we end up at R. So remember, this is the result of doing that integration. When you evaluate your integral, it's final minus initial. Here final is R. Here initial is R0. Now what about part 3 here? It looks the same as this, except now our initial is R and our final is R0, because we start from here and we end up there. Final minus initial. Final is R0. Initial is R. So look what happens when I add up all my work to get my total work around this integral right here. So the total work around that closed loop would be W1 plus W2 plus W3 plus W4, because those make up all the sides of this. But look, as I pointed out, 2 and 4 are both 0. That's 0, that's 0. W1 is minus Q QT over 4 pi epsilon naught, 1 over R minus 1 over R0. Work 3 minus Q QT over 4 pi epsilon naught, 1 over R0 minus 1 over R. So the leading terms here are the same. What's in parentheses has been switched. And if you take a look here, I see a minus 1 over R and a plus 1 over R. Those cancel. I see a plus 1 over R0 and a minus 1 over R0. Those cancel, and so you get 0. So what that means is the electrical force is conservative force. So the Coulomb force is conservative. Now what that means is this: if it's conservative, we can define a potential energy. Okay, so we can talk about the potential energy. So how do you get to that? Well, I want you to think about the same thing that we were doing here. We started our little charge off at R0, and we ended at R, except now I want R0 to be infinity. I want to take this thing out way, 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 way far out. Now, if it's infinity away, if I look at the force, that would be 1 over infinity squared. Now, 1 divided by infinity is 0. Okay, that's, from a limit standpoint. So what that means is that when R naught is at infinity, my force at that point is 0. And if there's no force, there's no potential for changes in motion, which means that at that point, my potential energy out there, my potential energy out at U naught would be equal to 0. No potential for motion, no potential energy. Or no potential for changes in motion, rather. So what I'm going to do is I'm going to take this equation for work here. And for R naught, I'm going to put infinity. Well, as I pointed out, this is 0. So this right here would be the amount of work that you would have to do to take a charge that's set out infinity and bring it towards here. Well, it's not the amount of work that you would have to do. This is the amount of work that's being done by, the Coulomb force trying to push it away as you do it. So here the work would be minus, qt over 4 pi epsilon naught 1 over r. But look, we know from University Physics 1 that when you do work, you can cause a change in kinetic energy. We also know that if you're dealing with a conservative force and energy is conserved, that's the same as the change in potential energy that you would see. So here, let's look at the change of potential energy. Well, potential energy, that's final minus initial because there's a change there. I've done the work. The work would be minus big Q, Q sub t over 4 pi epsilon naught 1 over r. Now out at infinity, which is where U naught is, because there's no force, there's no potential energy, which means that to bring it from infinity to there, your potential energy at this new point right here, your U there, there's a minus sign there, there's a minus sign there, they cancel, is this. Okay, so this is your potential energy. And in general, we say that due to a point charge, in general, the potential energy is 1 over 4 pi epsilon naught q sub t over r. So this is something that you can write down and you can use. But it turns out that this, I'm not going to say is of limited use, but is not used as frequently as something that is very closely related to it. Now, you'll notice that I bring up test charge, test charge, test charge. Test charges, like I said previously, are used to probe, like for example, the strength of an electric field. You take a known charge and you put it in the presence of an unknown electric field. You calculate the force. You use F is equal to QE to figure out what E is. So these are tools. So what I'm going to do is I'm going to take that U and I'm going to divide it by Q sub T. When I do that, on the right hand side, I have 1 over 4 pi epsilon naught Q over R. Now this right here deals specifically with the charge at the center. Okay. Of whose properties would we be interested in checking? Potential energy divided by charge is called voltage. It's also called electric potential. It has the units of volts. Okay, abbreviated V. So you can see where there can be a little confusion here, since the symbol for the concept is the same as the symbol for the unit. And as a consequence, sometimes instead of writing V, and by sometimes I mean usually, we use something called phi, which looks like that. And that's the same thing as voltage. So if you were to look in a different book, you might see this used along with this. And so for a point charge, this is the voltage due to a point charge. And it turns out that we can use this when we take the step from talking about discrete individual charges to charge distributions by making the substitution of like dV equals 1 over 4 pi epsilon naught dq over r, where if you're dealing with a line charge, that's lambda, dl. If you're dealing with an area charge, dq would be equal to sigma times dA. And if you're dealing with a volumetric charge, or a charge volume, if you will, it would be rho times, I hate to use V, dV. I'll put little bars over it like that so it's clear it's a volume. So this is where you would make that transition, and then you could use this in much the same way as we use the, the definition of the electric force to find out what the force was, above a loop of wire and things like that, when we're talking about stuff in Chapter 5. So that said, now we actually have a pretty useful relationship here, because what this does is to give us a relationship between potential energy and voltage. And voltage is something that you can measure very easily. They have these things that are called potentiometers or voltmeters. You can pick one up at Ace Hardware or Lowe's or whatever it is. It's got two little wires on it, and use it to measure the potential difference between things. And the reason why you care about the potential difference is because we know from conservation of energy that the potential energy isn't all that interesting. It's the difference in potential energy that causes changes in motion. This right here, through the work energy theorem. So that's the thing that's the most useful to us. Okay? But conveniently enough, we have a very easy relationship here between potential energy and voltage that looks like this. The difference in potential energy between 2 points in space is equal to the charge that you're trying to move between those 2 points and the difference in voltage between those 2 points. And this is a very useful equation to have. Okay? Now, that said, I'd like to go back and take a look at our work integral. All right, so if you remember, this is our work integral. Now what I'd like to do is, instead of looking at F sub E as a point charge, I want to relate it to a field, because we know the force that a charge experiences when placed in an electric field looks like this. So check this out, right? So here, the relationship between the force and the electric field is just a number. It's just a scalar relationship between it. Q could be positive or negative, and all that does is to switch the direction of the force. But it's a scalar. It's a linear relationship between these two. And so what that means is that if you look over here where we proved that the electric force is a conservative force, what that also means is that the electric field is a conservative field. Okay? So the electric field is conservative. It's a conservative field. And as a consequence, what I can do is to relate that to work and potential energy. Okay? So F sub E would be Q times E vector. dr is part of the line. Sometimes it's called dl. Now, if I were to divide both sides by Q, what I have over here, if you remember our conversation about the relationship between voltage and potential energy, what I have here is minus d voltage. So dV is equal to minus E dot dr. If you integrate both sides, on the left-hand side you get the difference in voltage between 2 points in space. What 2 points in space are they? Well, when you integrate E dot dr, it would be where you start and where you end up. So now we have another way that we can calculate voltage, and in this case, all we need to know is what the electric field looks like in order to figure out what the voltage is, or the difference in voltages between 2 points. Okay, so as a simple example, I want you to consider an infinite sheet of charge. So if you remember infinite sheets of charge, we know that you have a surface charge density. We'll say in just this case that rho here is positive. It's charge per unit area. And we've calculated the electric field, for positive distributions of charge, this electric field would point out like this, and it's constant. It's constant. It also points to the left-hand side. It's constant here, and it looks like if I were to call this the x-axis and I were to call this sort of the y-axis right here, it's going to look like rho, or sigma rather, over 2 epsilon naught. Why did I reverse that? There, sorry about that. X hat. Okay? So what I'd like to do is to find the difference in voltage between, we'll say here, the 0, and here, which I'll call x away. Okay? So, delta V here would equal to minus the integral from 0 to x. I'm starting at 0, ending up at x away, of E dot dr, noting the fact that dr is going to be dx x hat, and also the fact that E is equal to sigma over 2 epsilon naught x hat. When I do the dot product between these two things, the x and the x point in the same direction, which means that my integral that I need to do looks like this. Sigma over 2 epsilon naught dx. Super easy to do. Everything there is constant except for the dx. When you integrate that, you get x. You evaluate it from x to 0, and you get minus sigma x over 2 epsilon naught. Okay, so how does the difference in voltage vary from here to here? It depends upon how far away you are. The further away you are, the bigger the difference in potential, which makes sense because it's pushing you the whole way, so the force is exerted on you the whole way. So if you know what the electric field is, you can talk about not only the voltage, but you can also talk about how that relates into the force and the potential energy. All right? So it's a very useful thing. Now, as an example, what is the voltage 10.5 centimeters away from a 5.0 times 10 to the minus 6 Coulomb point charge? So let's draw us a picture. It's a point charge. And since it's a point charge, we already know what the equation for the voltage looks like. So here's my point charge right here. I'm going to call it Q. Somewhere over here, we are 10.5 centimeters away. This I'm going to call R. That's because it's a radial distance away, like that. So I'm given Q is 5.0 times 10 to the minus 6 coulombs. I'm given R is equal to 10.5 centimeters, which is the same thing as 0.105 meters. And what I'd like to find is just the voltage at that point. Now, the voltage at that point is 1 over 4 pi epsilon naught Q over R. It's that easy. So if I plug stuff in, that's going to be 5.0 times 10 to the minus 6 coulombs on the top. On the bottom, I have 4 pi. Epsilon naught is, I want to say it's 8.85 times 10 to the minus 11th Coulomb squared per Newton meter squared. I just want to verify that. Excuse me. Minus 12th. It's a good thing I verified that, huh? 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. And then you have R. Okay, so R is 0.105 meters. So what's your voltage here? I'll get my calculator, which is here somewhere. Oh, I think my daughter ran off with it. Yep, that's what happened. Oh, I'll just figure it out. Actually, I take that back. I think I know where it's at. Aha, there it is. She has her little cubby holes around here. She likes to hide stuff. It's like a little magpie. So 5 times 10 to the minus 6 divided by 4 times pi times 8.85 times 10 to the minus 12th times 0.105. And so what I get here is that at this point in space is 4 point, if I keep the sig figs, 4.3 times 10 to the 3, 4, 5, 10 to the 5th volts. And that seems like a tremendous amount of volts, but remember, we only care about the difference in voltage. Okay? That is what's useful to us when it comes to determining changes in motion, which is, ultimately what all this is about. You find a force, and the force moves stuff, and you want to relate that force to how that motion happens, through equations of motion. So, here's another example. What is the potential difference between 2 points in space separated by 10.0 centimeters if there is a 150 Newton per Coulomb field that goes between them? If an electron were placed at rest at point A, what would its velocity be at point B? So, we are given a separation distance, which I'll call delta x, since that's along the x-axis, of 10.0 centimeters, or 0.100 meters. We're also given a field, which in magnitude I'm going to call E. It's 150 newtons per coulomb. Okay? I want to know what the voltage is between these 2 points in space, what the potential difference is. And I also want to know if an electron were placed right here, what would its velocity be at point B? Now, so given that we're dealing with an electron, which means our charge, Q, is going to be 1.6 times 10 to the minus 19th coulombs. That's the charge of the electron. We're also ultimately going to need the mass of the electron, which is 9.11 times 10 to the minus 31st kilograms. Okay? What we'd like to find is the difference in voltage between those 2 points in space and the velocity at point B. Now, the velocity at point A is our initial velocity, which is 0. So, to do this, what I'd like to do is to use the equation that we came up with right here. All right? So, that equation says that the difference in voltage between 2 points in space is equal to minus the integral from the first point to the second point of E dot dr. Now, dr is this way. And in fact, it's really just dx, because our electric field is constant. So, if you're dealing with a constant electric field, and the path that your charge is taking when it goes from point A to point B is a straight line, this integral really is just this. Where delta r is the direction. It's the displacement. So if you look here, as drawn, our electric field goes this way. But our charge, if you think about this, we're putting a negative charge here. You know, F is equal to Q times E. If we have a negative charge, the force that it experiences is going to be in the opposite direction of the electric field, because Q is negative, and that flips the direction around. So we expect to force this way. Okay? So delta R is going to be delta X, X hat. So what you have here is an electric field that points in the negative X hat direction. It points this way. But you have a displacement that points in the positive X hat direction. So when you do the dot product here, you get a positive number. So this is just going to be the magnitude of V times the magnitude of delta R, or in this case, delta X. So that's 150 newtons per coulomb times 0.100 meters. Super easy to do. 15 volts. Okay? So the difference in voltage, or the difference in potential between here and here, or between here and here rather, is simply 15 volts. Okay? So like I said, it's the difference that's the big thing. Now, here's the deal though. We know the relationship between voltage, potential energy, and charge. So, the difference in potential energy between those 2 points in space is going to be Q times delta V. The work energy theorem says, though, that when something does work on an object to cause it to move, you see a corresponding change in kinetic energy. You also see a minus the corresponding change in potential energy. So this is the same thing as minus delta K. Now, K, if you remember from University of Physics 1, is 1/2 mv squared. Our initial kinetic energy is 0 because it starts at rest. So here, K minus K naught on this side, I'm going to move the negative to the other side, is minus Q times delta V. K naught is 0, right? So this is 1/2 mv squared. That V is going to be at point B. That's equal to minus Q times delta V. So here, our velocity at point B is going to equal to minus 2Q delta V over M. And you have to take the square root of it. So if you plug stuff in, Q was 1.6 times 10 to the minus 19th coulombs, but it's negative because electrons are negative. I should have pointed that out there. Sorry about that. It's negative. Our difference in voltage is 15 volts. And the mass is 9.11 times 10 to the minus 31st kilograms. So when you do this, you get see here 1.6 times 10 times 10 to the minus 19th times 15, then divided by 9.11 times 10 to the minus 31st. I get 2.3 times 10 to the 36 times 10 to the 6 meters per second. So, 2 sig figs here, 3 sig figs here, 2 sig figs in our voltage, one of the things we're trying to find, and 2 sig figs in our velocity. Now, so, let's do another example. Okay, so in this example we have an electron gun, which is designed as shown. Now, electron guns fire electrons. That's what they do. And typically what happens is you inject in your little electron here, and because of the direction of the electric fields and because of where you put it, it picks up an acceleration while it sits here between these plates, and it's fired out this way. Now these are, for all intents and purposes, you can think of them as infinite sheets of metal or infinite sheets of charge. And so what that means is the field that sits between these plates is constant, because if you remember, back, let's see here, I believe, when we were talking about, the electric field due to a long sheet of charge or an infinite sheet of charge, it's constant. It looks like sigma over 2 epsilon naught. So here we have our electron gun, and it's going to fire this electron out very quickly. Now, typically, what you're aiming at is some sort of screen. In the ages before flat screen TVs and flat screen monitors and things like that, you may have seen these enormous TVs that had huge tubes in them, and that's what these were. Those were electron guns. The screen that the electrons were being fired at had phosphorus on the back, broken up into little pixel pieces, and when an electron would hit the phosphorus, it would cause the phosphorus to actually fluoresce, and it would scan up and down, something like 60 to 120 times a second. Actually, I think 29.96, I believe, somewhere around there is like the normal refresh rate for traditional TV, so probably about 60 times a second approximately. Up and down, up and down, up and down, building your picture, and that's how you would see it, would be, what was fluoresced. So what we have here is a known voltage that sits between, or a known electric field rather, that sits between these two plates, we know that the field has a magnitude of 270,000 volts per meter. Now, if you take a look at these units are different than what we've used for the electric field previously. You know, for example, here, let's see, let me find a good example of it. Oops. Actually, probably a previous problem. Here we go. Yeah, so here you can see it's newtons per coulomb. But if you look at, for example, this definition of voltage, on the left-hand side you have units of volt. On the right-hand side you have units of the electric field, and then you have a length. So you could write the electric field also as volts over meters. And that's actually the preferred way typically to write it. So as I was saying, we're given the strength of the electric field that sits between the plates. As drawn, it would be, you know, obviously in the minus y direct or minus x direction. We'll get to that here in a second. And so we also know the plate separation right here. I'm going to call that D. So the separation between the plates here is 1.0 centimeters. So D is 1.0 centimeters. And we're trying to find a few things. We want to know what the kinetic energy would be of the electron when it left the plates, basically when it stopped accelerating. I also want to know what percentage of the speed of light this thing is traveling at when it leaves. So we want to find the kinetic energy and also the percentage of the speed of light, which I'm going to write as percent %C, because C is, you know, typically what we use to denote the speed of light. Now we're dealing with electrons here, which means we know additional information. We know the charge is minus 1.6 times 10 to the minus 19th coulombs. We know the mass of the electron, which is 9.11 times 10 to the minus 31st kilograms. We're going to assume that the electrons are injected into these between the plates with an initial velocity of 0, so we know V0 is 0. We also know the speed of light, which if you look that up is 3 times 10 to the 8th meters per second, which you can treat as exact. So that said, we're going to solve this problem in much the same way as we solved this right here. So if you look again, you know, at the definition of voltage, delta V being minus the integral from point A to point B of E dot dr. And note the fact that between the plates the electric field is constant. And here dr just really means, you know, the displacement here between the plates. You can write this the following way as minus, you know, E dot delta R. Now, so let's talk about directions. So here, the electric field as drawn, and let me clean this up just a touch so I can you know, kind of make it a little bit clearer here. So the electric field is drawn points down the minus x direction. So if you think of this as x and y, so this is y, this is x, here's our 0. So here E is going to point in the minus x hat direction. But this thing is going to be accelerated this way. Now we know that because it has a negative charge. If it had a positive charge, the force it experienced would be in the same direction as the electric field. Here it has a negative charge, so the force it experiences is going to be anti-parallel of that. So it's going to send it zinging out this way. So what that means is that as it leaves, the displacement that it's covering is going to be in the x hat direction. So when you actually do this dot product here, you have a minus magnitude of E, magnitude of delta R, and then a minus sign that comes as a consequence of doing the dot product, which makes this overall plus. Okay? So this is the potential, the electric potential, or the voltage. All right? So I'm going to write these magnitudes as just E times D. Since delta R is D, it's the separation distance. Now, we also know the relationship between potential energy and the voltage. Okay? Remember, kinetic energy, or at least the change in, is equal to minus the change in the potential energy. And we know through, right about here, I believe, right here, actually I think we probably, yeah, here we go. Right here, we know the relationship between voltage and potential energy. Okay? So, here the test charge is the electron. So, let me go down here a little bit more, right here. So here, delta U is going to be Q times delta V. But that's going to be the same thing as minus delta K. All right? Now, so delta K is the change in kinetic energy. That's K minus K naught. Our initial kinetic energy is 0 because it's being injected in at an initial velocity of 0. And on the right-hand side over here, I'm going to move this negative over here, by the way. You have a minus Q times delta V. All right? Which is going to be minus Q times the magnitude of the electric field times the distance between the plates. So our kinetic energy here is minus a 1.6 times 10 to the minus 19th coulombs. The electric field is 270,000 volts per meter. And the distance between the plates is 1.0 centimeters, which is the same thing as 0.010 meters. Okay, so 0.0, whoops, yeah, right, 10 meters. I was getting ahead of myself. So let's see. You do this, you get negative times a negative makes a positive. So really this is just 1.6 times 10 to the minus 19th times 270,000 volts per meter times 0.010. So what I get here is 4.32 times 10 to the minus 16th joules. Now this is a tremendously small amount of energy, which is the reason why in the problem what we want to do is to express the energy in what's called an EV. Okay? Now an EV is an electron volt. So 1 EV is the same thing as the energy that it takes to make 1 electron travel across 1 volt. 1 volt of potential difference. So 1 EV is 1.6 times 10 to the minus 19th joules. So I'm going to convert this to EV. 1 EV, 1.6 times 10 to the minus 19th joules. And you can see how if I were to know that straight off the bat, the math becomes easy, right? So let's do that. I'm going to divide that by 1.6 times 10 to the minus 19th. And I get 2,700 electron volts. Or 2.7 keV. Now, the electron volt is the preferred unit in many applications when you're dealing with individual atoms or individual electrons and things like that. And that's because the energies that you end up with are so small that constantly writing, times 10 to the minus 19th and things like that is just a lot of trouble. So we use the EV instead. So here's our answer 2.7 keV, or 2700 electron volts. Now the next thing we want to do is to find out what percentage of the speed of light this electron would have as it traveled out. Now to do that, we're just going to use the equation for kinetic energy, 1/2 mv squared. We just want v, so v here is going to equal to the square root of, excuse me, 2 times k over m, or the square root of 2 times, k is 4.32 times 10 to the minus 16th joules, and m is the mass of the electron, okay, which is 9.11 times 10 to the minus 31st kilograms. So square root of 2 times 4.32 times 10 to the minus 16th divided by 9.11 times 10 to the minus 31st. And I get 3.1 times 10 to the 7th meters per second. So if I want to find out what percentage of the speed of light this is, the percentage would be the speed that I have divided by the speed of light, which is going to be, 3.1 times 10 to the 7th meters per second, divided by 3 times 10 to the 8th meters per second. So when you do this, you're going to get about 10%. So this is 0.1, make sure there's no weird, 0.10, or about 10% the speed of light. So this right here is generally considered to be the beginning or the cutoff for when you start to have to move away from the mechanics that we talked about in University 1, and you start talking about the mechanics that describes things that move substantial percentages of the speed of light. That is special relativity. Okay, so we're not going to do that. Hence, the cutoff here of 10% the speed of light. So these are, just starting to be relativistic electrons, which in part is one of the reasons why, back in the day, if you watch TV with your face glued to the screen, there was some concern that you might get, some radiation damage. I'm not sure how true that really is these days. You don't have to worry about that about flat screens and, CRTs, which are cathode ray tubes, which is basically what this is an electron gun. Those things really aren't used in TVs anymore. So, this is a simple example. So in this example, what I want to do is to use the equation that I had mentioned earlier, that's for continuous charge distributions. That is dV is equal to 1 over 4 pi epsilon naught dq over r, to find out what the voltage is at this point right here. Now let's talk about what dq and what r are. So dq is basically us adding up all of the charge along this when we integrate it. So if you remember, lambda is equal to q over length, because this is along a line, it's just a hoop. So here, dq is going to be lambda, we'll call it dl. And L here, dl here is just along the circumference, it's an arc length. And as drawn using a radius of a for our hoop, dl is just going to be a times d phi, with phi being the angle here, between x and y. All right, so phi goes around that way. So that's dl. Now what about r? Well, r is the distance from the point that we're looking at to the point of interest. So here, if you think of integrating around it, it's going to be along the hoop. So this right here is r. Now, R has a base of A and a height of Z. So if you use the Pythagorean theorem here, it's just going to be Z squared plus A squared. So if I take my equation here and I integrate both sides, dV on the left-hand side, on the right-hand side, I'm integrating 1 over 4 pi epsilon naught dq. Dq is lambda dl over r. Okay. And we're going from, we're going to go from 0 to 2 pi because we're going to be going along this right here. The left-hand side is just the difference in voltage. That's what we're trying to find. The difference in voltage from the edge, from the hoop itself to the point in space right there. And on the right-hand side, there's a lot of constant stuff here. We'll get to that here in a moment. I'm going to just go ahead and pull out the 1 over 4 pi epsilon naught. And so we're going to integrate from 0 to 2 pi of lambda. Now dl is a times d phi. And r is the square root of z squared plus a squared. And here's the deal. All of this is constant except for d phi. When you integrate d phi, you just get 2 pi. So this is going to be the same thing as 2 pi lambda a over 4 pi epsilon naught, the square root of z squared plus a squared. It should be a squared. Now, again, 2 pi cancel out, pi here, you get a 2 there. So your voltage, we're just going to write it as V. A lot of times, differences in potential are just written as V because we choose a reference point that's 0. This is just lambda A over 2 epsilon naught, the square root of z squared plus a squared. Excuse me. So this is your potential right here. So as you can see, as you vary the length of z, as you make it higher, that changes this. As you make your loop bigger, that changes this. Okay. Now, so that's it for the first video. In the next video, I'm going to talk about the relationship between the electric potential and the electric field a little bit more closely, specifically how you can get the electric field from potential, because it turns out that potential is very easy to measure. As I mentioned, earlier, you can use something called a voltmeter or a potentiometer to measure voltage very easily. So it would be nice if there was a way to go between V and E, and there is, and we'll talk about that in the next video.